Hello. How's everyone feeling today? I know it's Friday, but it's an exciting day because we're here at EthAtlanta. Yeah, so first off, I want to thank everyone for coming out, and I want to thank Parallelism for putting this on. I'm Brandon Iglesias. I'm the head of product at Storj Labs.
And I'm Dominick Marino. I'm a solution architect at Storj.
And today we are going to be talking about building a public good for specifically around Enterprise Ethereum, but really anyone can kind of use our services. So you might learn how you could leverage it with your own applications or in the hackathon. We need the remote. Aha. Okay, so hit the next slide for me. So this is just going to be a quick agenda of what we're going to be talking about today. We're going to just do a quick overview of the product that we built, which is decentralized storage. We're going to talk about some of the use cases and how you might be able to leverage decentralized storage for your applications. We're going to be talking about the performance and scalability aspects of decentralized storage and why they're so advantageous. We're going to give an example, specifically chain data snapshots, downloading the full Ethereum blockchain in 24 minutes or faster, which is, I've been running Ethereum nodes for years, and syncing Ethereum nodes can take a lot longer than 24 minutes. And then after that, we're going to go into questions and answers, and this is definitely going to be quite an interactive session. So please, we're going to pause at some of these slides, and if you have questions about the architecture, or if you have questions about how the system works, or just random questions, please feel free to ask. We're both motorcycle gearheads, so if you have motorcycle questions, you can also ask those.
All right, so let's kick off how it works. Brandon is going to go through this section of the deck, and then I'll pick up the next slide.
That sounds good. Okay, so decentralized storage, how does it work? So the way that we've architected decentralized storage is we have three major peer classes in the network. We have uplinks, which are people who have huge amounts of data, people like the Ethereum blockchain. We have satellites, which tend to keep track of the metadata on the network. And then we have storage node operators who basically have a ton of underutilized resources that they want to monetize. So if you think about these three different peer classes in the network, essentially what they do is they interact with each other to make it so that you can store large amounts of data without us owning a single hard drive. So Storj Labs, the company, doesn't own any hard drives, but there's about 15,000 nodes on the network who all dedicate different levels of resources. Some people dedicate 2 terabytes, some people dedicate 20 terabytes, and so on and so forth. And all of these individuals on the network are compensated depending on resource utilization and depending on how much data is uploaded and downloaded from the customers. And I think this is actually probably a good place to pause.
I'm going to loop back through it just very briefly. Again, we've got the uplink. That's how you interact with our network. You, the consumer, will use that uplink via a bunch of different modalities to send that data into our decentralized cloud. Now, that satellite is the responsible party, right? It remembers what's going on. And those node operators are, we're in the teens of thousands now of independent node operators that are statistically uncorrelated, so that when we take your data and erasure code it, which you've encrypted it, by the way, and send it out into the world, it's truly decentralized, and it's over a device, a diverse array of devices around the globe. So does anyone have any questions on that structure of the network on the peer classes? Anyone lose any data? Anyone ever retrieve data far too slowly? No? Okay. So we'll jump into the next slide here, and we'll talk a little bit more about how it works. So as an architect at Storj, I always get to say, Brandon has a lot of fun in product, but I get to have like all the fun. I get to play with all the toys. I get to work with all the prospects and really find that good fit. So when you're putting data onto our network, you have the option of running that uplink, that utility. Think of it as an uploader. You are then the custodian of your encryption keys. I'll repeat it. You are the custodian of your encryption keys, not us. That means if you lose your encryption keys, we can't restore your data. That's a really, really good thing. So when you do that, when you upload a file to our network, let's imagine that the file is 64 megs. It's a nice, easy number to use. It happens to be our block size. Well, when you upload that file, you're going to encrypt it with your encryption keys, and then we're going to take that file and split it into 80 pieces. Now, we send those 80 pieces out to statistically uncorrelated nodes around the globe. Thus, you have a bunch of parity on the network. It's very similar to how RAID works in the storage arrays we used to use, or we use in centralized solutions today. So when you go to pull that file back, well, you're only going to need 29 of those 80 pieces to reconstitute your file. And what's really cool about that is you can lose a whole lot of nodes around the globe and not have any impact in performance or the resiliency of your file. Now, what differentiates us from a lot of other offerings in the decentralized storage space is the fact that we automate that repair. So you go, well, what happens when 2 or 3 or 5 nodes drop off the network? Our satellites are constantly monitoring, auditing the health of the network and the health of your file. Now, again, we don't know what your file is, but we know that 2 or 3 pieces are missing. So what we'll do is we'll go out, grab that encrypted file, and repair it. And you never know or care. So there's an entire layer of your application, your decentralized application, that you are now no longer responsible for architecting and maintaining. We take care of everything. You just pay your storage bill, and you get to use decentralized, reliable, performant, and high-value storage without any of the complication. Does anyone have any questions on the erasure coding aspect, the encryption, any network fundamentals? No? Nope. So we charge $4 per terabyte per month for storage. So if you store 1 terabyte and you store that terabyte for a year, you're paying every month. And then we pay we charge $7 per terabyte of egress. And then we just do a flat scale. So if anyone has ever procured IP transit globally, you know that North America and the European Union is fairly affordable. But you go into South America or APAC, right? Or Seoul, specifically in APAC. And all of a sudden your wallet is now, well, lighter than it used to be. We charge $4 and $7 globally. And we have ingress points to the network if you do want to use a hosted gateway versus natively integrating into the product. And we have those points of presence currently in North America, specifically Toronto. We have a point of presence in the European Union in Frankfurt, and a point of presence in Asia Pacific in Singapore. With that,
I do want to add something to that. So we charge $4 per month for storage, but that's multi-region storage because your data is distributed across the network of nodes that we have around the world. So it's like if you were going to do multi-region data storage on AWS, you're typically paying 2 or 3 times the normal AWS fee just because you're paying twice the amount if you're doing multi-region in 2 places. So we're multi-region and still $4. I mean, it's pretty cheap.
and we have extra slides and performance and resiliency, so keep them coming.
We had one question over here. So the question was,
you mentioned like having like 80 and then like only using 29 and still having data. Like,
so the concept of erasure coding, which has been used in RAID forever, we put extra parity out into the network. And without getting into too much detail, know that we put 80 pieces out, but you only need 29. So parity, what's the best way to explain parity?
I would say like, yeah, so like RAID sometimes uses replication versus parity. And like when you replicate drives, that basically means that you have 5 hard drives, and if you have 5x parity or 5x replication, each of those hard drives will store the exact same thing. We don't do that because replication is really expensive, like literally mirrors of the data. So the erasure encoding that we use allows us to create unique pieces of a file, and you only need a subset of the superset of those pieces to reconstruct the file, but it's any of the pieces in the subset. So when you have a file that is about 10 megabytes, it gets split into 80 pieces, okay? But you only need 29 of those 80 pieces, and it can be any 29. Right, so let's say all the people in this audience are storing 1 piece for a file. You know, if some of you walk out of the room, it's okay. It doesn't matter which of you walk out of the room, as long as we have the minimum number of pieces required to reconstruct the file. And when we were talking about the architecture previously, the satellite, which is that layer that sits kind of on top of the nodes and the uplinks who are uploading the data and storing the data, the satellite is responsible for auditing the nodes on the network and making sure that they're keeping the pieces that they should be keeping. So the satellite kind of acts as a puppet master and keeps track of the metadata to make sure that as a client, right, if I'm using S3, I want to store my data, walk away for a year, and then download it when I need it. You have the same advantage on our network because the satellite is just maintaining the availability and durability of all the files on the network.
Simply put, you don't have to worry about it. Yes? Absolutely. So we do that automatically. It's an audit process that runs on a continual loop. So we're always doing that. I forget the exact number right now.
It's 56 pieces. So if you upload like a 10 megabyte file, there'll be 80 pieces uploaded to the network. When it gets to 56, the satellite will download some of those pieces. When it downloads those pieces, it can't see it because their client-side encrypted. So it's downloading blobs of data. But then we'll perform a retell and erasure repair. We'll upload new pieces, and that file will go from 80 to 56, get repaired, go back up to 80. So every file that gets uploaded to the network actually has a natural churn. And we have graphs over the last 3 years of files that have been uploaded, gone up with 80 pieces, gone down to 56, and so on and so forth. It's just a natural decay and replenishment.
The key, though, is you never worry about it because you don't have to manage it.
Exactly.
Just done. And we pay within our economic model. We've built in the cost of repair and thus have built an economy for which the node operators are consistent. They are reliable, which reduces the repair need because they're incentivized to stay on the network. So it's a careful balance to build that economy, but we've done quite a good job at it. Ready to hop?
Yeah.
All right.
Okay. So, yeah, I guess next we could talk a little bit about the ease of use. So as an uplink or someone who has tons of data, I used to be an engineer and I used to integrate with APIs and different libraries. You can do the same thing with storage, DCS. So you can integrate with one of our native libraries, or you can use an S3 gateway. And then we have a number of different tools that you can use, such as rclone or Duplicati, that have native integrations as well. Do you want to add anything to this, Tom?
Oh boy. Yes. So we're going to get into the performance and the resiliency. So there are different ways to interact with the network that have different benefits, right? There's always a better way to do something, and it's really specific to what you're trying to accomplish. So we found that some processes even benefit from two ways of interacting with the network. So for instance, when you upload to the network, and let's call out that extra parity, the 29 of 80 pieces, well, that means when you're uploading natively, you have to upload 2.68 times more data. You upload a gig, you're actually uploading 2.68 gigs. Now, that's generally not a problem, but let's imagine you don't want to do that. Well, we host a gateway, which has us do the encryption and erasure coding. We don't record your encryption keys, but we do the encryption for you. It is completely an option, and that allows you to upload at a 1x, right? 1 gig is 1 gig. But when you're downloading, it's always best to go to the nodes directly. So running that uplink and pulling your pieces back in parallel is always faster. And we've demonstrated speeds recently upwards of 6 gigabits of throughput from a high value decentralized object store, which if anyone's a network engineer or they have experience in that area, I mean, we're talking we're talking hundreds of megabyte throughput, which exceeds even the write rate of a lot of disks from a decentralized platform. So there's an option for everyone. And if today you're using something that is S3 compatible, you can plug that in. It's 3 lines of code, right? It's your endpoint, your access key, and your secret key. And if you wish to dive in a little deeper with the native integration, which for the decentralist in the crowd is most certainly the way to do it. We have libraries for many languages. So we're here to support you, and if you need help, let us know. Jump to typical use cases. So, boy, I've got some favorites here. we've been doing a lot of projects with customers recently in the video streaming and storage space. So a concept that's very important to understand is we talked about 64 meg block sizes on the network. That means if you're going to put something on our network that's 64 or 10 megs, it's going to be one thing. It's going to be one segment. But if the file is bigger, it's going to become multiple segments. And the advantage of multiple segments is you get 80 pieces per segment. So all of a sudden, if you're uploading, let's say, a gig file or a terabyte file, you're getting to hundreds or tens of thousands of pieces on the network, which means when you go back to stream it, you have the ability to survive viral content. So the more pieces that are out there means the more nodes that are supporting your particular file. And we actually have a great streaming use case that we can demo to anyone that wants to see it after this. But you can stream 4K 60 frame video from the decentralized cloud without any buffering. Like, we do that today. We host a lot of our own training videos, a lot of our information videos. It's not a CDN, but it acts like one to a point. So if you're hosting media content on your site and you want ultra low cost egress, that is the ability to send that data out to the world at low cost, this is a great intermediary solution. And if you want to combine it with a CDN, we work great with Fastly to buffer at the edge, meaning if you have the next viral, forgive me, cat video, you can utilize a combination of us and a CDN partner like Fastly to serve it to an unlimited number of people. Really, cloud native web application, storage apps. Storage is huge for us. It's kind of in the t-shirt. So what I mean by that is MSPs love the service because they're always looking for performant, low-cost storage that is resilient. So we will sign an SLA with you that meets or exceeds what, for instance, a hyperscaler will do. We have 11 nines of durability. We've never lost a file, but we guarantee 11 nines of durability. In addition to, we guarantee, is it 99 point? Yeah, it's four nines of availability of your file for the first try. Yeah, so it's a great SLA and it meets most corporate requirements. When it comes to large distribution of files, that really goes along with video, right? It's the same thing. If you're gonna download a large file, it's very equivalent to streaming video. And then, did you want to add anything to it?
Yeah, so the one that we're going to talk about here in a second is the blockchain Fastsync use case, which I think a lot of you might find interesting. So should we dive into it?
So I am curious, who in the crowd runs a Geth node or runs an Ethereum node of any type? Okay, we got one, we got two. All right, so we'll talk directly to you in this next part. So, we'll do performance first? Okay, got it. Did you want to dive into performance?
No, you go ahead.
Okay. All right, so everything we do is multi-region. There's not a single copy of anything we're doing out there. And when we talk about performance and scale, you can see an example. This map is actually from the community. We like it so much, we decided to use it. And it shows the density of storage nodes. European countries really have fair bandwidth policies, so we find we get a lot of adoption there because they get unlimited upload, which is very important for our network, because if you're a node operator, how do you make money? Well, you store files and you give them back, right? We pay you to store, we pay you to upload. So Europe's very popular, as in the United States, we have some more restrictive ISP limitations. That is, your typical Xfinity tends to cut you off at a terabyte or two. Now, when we talk about the performance and scale, what's really interesting about our network, and I've championed this with a contact at the University of Edinburgh who is working on a supercomputer project where they're sharing these enormous data sets. So what we've done is, remember we've got the segment, and remember we need the 29 pieces of the segment. Well, when you go to download a segment, it's going to download that segment in parallel. So all those pieces that you need come down at the same time. But what gets really cool is if you have a big file, it might be made up, let's just imagine it's 10 segments, right? So all of a sudden you've got 10 segments, and traditionally those would download serially. So you'd have a parallel effort to the next parallel effort to the next parallel effort. And what's really cool is recently working with product, working with customer feedback, we've enacted segment parallelism. And it sounds kind of complicated, but the concept is this. Please give me all of my stuff at the same time, please, right? Now, there are limits. You can easily take down your internet connection or overload your router if you type crazy numbers into it. But that's how we've gone from demonstrating speeds of, let's say, 50, 80, 100 megabyte throughput, and we've gotten to the multi-hundred. So we find that using a consumer laptop, think MacBook Pro, it's pretty easy to get above about 1500 megabit. I'm changing standards, but megabit is the best way to explain it when comparing it to how your ISP, for instance, advertises the speed. So we can go about 50% faster than a gig internet connection using consumer grade hardware, nothing fancy, no really cool servers. And that enables this blockchain Fastsync case that we're going to be demoing today.
I'll go to the next one.
Fantastic. You want to talk Volunteer?
Yeah. So when you're downloading a file from the network, a lot of you might question like, well, I only need 29 pieces. How am I actually downloading this file, right? Like Dominic talked about parallelism for pieces that are getting downloaded and parallelism for each of the segments that are getting downloaded. And part of the reason that we can do it so quickly is because we have this thing called long tail elimination. And essentially what that is like, hey, I only need 29 pieces, but if you're only downloading 29 pieces, then you're only as fast as the slowest node. So what we do is we actually download from more nodes because we have such a big pool, right? 80 nodes are storing a piece of your file. So we download from about 35 or 36, or you download from about 35 or 36. And when you get the 29 pieces that you need, you kill the other connections, you take those pieces, reconstruct them and decrypt them on the fly so that
you could call it a race to the end, right? You got everybody lined up, and the first 29 runners that make it in the gate won. And the rest of them, you don't need.
Yeah. So that's part of the reason that we're able to download data so quickly. I'll go next. And to the example. So if you want to try this out yourself, you actually can. We have two methods for you to try it out. You can download it via one of our edge services that Dominic was talking about, or you can download it with the uplink natively, which will get you way higher throughput and speed. But if you go to fastsync.storj.dev, you can actually go download the entire ETH chain state right now.
So it's from the 28th, I believe. It's the ETH, it's ETH chain state. Yeah. And we highly encourage you not to ever trust anyone else's chain state. So this is a demo. That being said, if you're running multiple nodes yourself and you want to replicate, this is most certainly the fastest way to do it. So we've got this thesis we put together here. You can see we're actually using a Vultr VPS just for full transparency. And there's 3 lines. And what we want to point out here is the traditional sync model. We all know that synchronizing an Ethereum node can take, well, I don't count it in hours. I tend to count it in days sometimes, particularly if it's an archive node. So what gets interesting here is you have guest snap, right, which is fast, and then you have us. And the difference here is, let's imagine you're running a full node. Well, how do you best replicate it when you trust the chain state? Well, you stop the node and you copy the database. You put it on your next node, you turn it on. Now, again, you only do that when you fully trust the source of the chain state. But if it's you or your organization, then of course you trust the chain state of the node that you're running. Now, what we've implemented here is massive parallelism. So on this Vultr, so Carl did it in, I think, 2 hours in the example that he was running here. But utilizing a virtual machine with 16 vCPU, and I believe it was 96 gigs of RAM, but I didn't get near the limit of that memory, I was able to bring a node up in 24 minutes. So depending on the compute power available, you can sync in, we've demonstrated 24 minutes. In full transparency, At a chain state, I think it was 368 gigs. It's 378 gigs, 368 gigs, right in that area. If you have flexibility in your compute and you can scale up and down the CPUs you have available, you could probably get that to 15 minutes. Now, how does an organization like Binance or a large player in this space actually replicate their nodes today? They've not told this to me directly, but you do it in a building on a really fast network, and then you take a box that says overnight, and the node flies on an airplane. So before this, your options were quite limited in fast replication and literally involved aircraft.
Yeah, I mean, syncing an ETH node from the beginning takes weeks, especially if you're doing it on consumer grade hardware. So being able to do it in 25, 30 minutes is incredible.
And that's what we feel. We've been enabled by Ethereum, right? Our economy for our product. It's how we pay node operators globally. And now this is kind of our thing we feel we can help the community with. So with the lack of proliferation in node count, right? As nodes get more centralized as Ethereum grows, this is a great way to ease the burden of running your own node. Anyone have any questions on that?
Go ahead.
So you're using Binance as an example. So you're saying that when they want to stand up another data center somewhere else, and they want to include every bit of history of every single transaction pair for whatever length of time that they've been running, this is, for them, would be the most effective option to put it in a airplane, have UPS take a hard drives.
Well, so until recently, the largest transfer of data that occurred on a daily basis was a company we call Netflix. And it was through the US Postal Service. And it was Blu-ray movies, right? 45 gigs per movie. So the most data moving in the world was literally Netflix. So it's hard to beat replication in a local environment. So you're in a local environment, you're gonna have 100 gig network. You're gonna have the best hardware. You're gonna have a bunch of NVMe disks. You're gonna have tons of compute, tons of memory. This is actually a viable alternative. Now, what is ETH archive nodes right now? 8 terabytes? It's something around that. And that's a lot. I mean, that takes, even at high speeds, that takes weeks to move. But when we're talking about hundreds of gigs, all of a sudden you get to take the airplane out of the equation. And that is most certainly how today, per my reading and conversations in the industry, archive nodes in particular are being replicated. Now, we're really focused on full nodes in this talk, but if anybody here wants to try to replicate a archive Ethereum node, I mean, I'll say I have the ability to provide some development credit and work with you. I don't have the resource myself to run one, but if somebody has a full archive node, boy, would I love an export of your chain state, and I would love to throw it up on the network and do some testing. So please see me if you have an archive node and you would like to experiment with it.
What's your payment options?
What was the question?
Payment options.
Oh, so we have a couple of payment options, but we only have 1 minute, so maybe we can cover that. We'll go over to your table.
Storage token and USD.
Yeah. So we're getting clapped off, but if you want to try this out, you can just go to that URL. We will also give you basically as much free credit as you want. If you're a developer or you're participating in the hackathon, we're more than happy to give you a bunch of free developer credits on our product so that you can use it for the next few months or however long you'd like. And if you want to learn more, you can go to storj.io or email me at brandon@storj.io or dom@storj.io.
I'm going to need that email now.
Yep.
All right.
Oh,
Thank
it's
you, Brandon.
Dominic.
Yeah, but it's fine. Thank you, everyone.
Great presentation.